Click the bell icon to get latest videos from Ekeeda.
Hello friends, this is the video from chapter number 12 where we are learning representation and description after we have covered the chapter image segmentation. For representation of the image regions that are readily available after segmentation process, we have the boundary following algorithm, the simple representation with the help of chain codes. We have the signatures, skeletons also. Now for descriptions, we have the boundary descriptors by the potential tools like the Fourier descriptor, shape numbers we have, and into the previous video we are also covered with the term texture to have the proper representation and further description of the region. Now in this video we are going to discuss about the another kind of a descriptor in this family by the use of moment invariants. So let us discuss this. So here we can start with our topic moment invariants. Now as we are having the image as a two-dimensional signal here, for a two-dimensional, first of all the continuous function we take representing as f of x comma y, where x and y being the spatial coordinates and f representing the amplitude level, the value at that particular location. Now in such a representation, the moment of order where it can be represented in the parenthesis p plus q can be defined by the formulation. Here we have m suffix pq computed as double integral. Both the integrals are limiting from minus infinity to plus infinity and they are operated over x to the power p into y to the power q into the two-dimensional continuous domain signal f of x comma y into the differentials with respect to x and y. Now this is applicable with the small p and q having the values that are starting at 0, 1, 2 and they can increase. Now the uniqueness theorem we know, and as per the statement of the uniqueness theorem, if f of xy is a piecewise continuous and has non-zero values only in a finite part of the xy plane, then the moments of all orders exist and the moment sequence that we can denote by m of pq as a suffix here in the pq is uniquely determined by the input function f of x comma y. Now conversely, m suffix pq uniquely determines f of x comma y. Now the central moments can be defined by the following formulation, where we have the denotion mu suffix pq computed as again the double integral ranging from minus infinity to plus infinity and computed over the bracket that is having power small p. The bracket is representing the difference x minus x bar here, whereas it has multiplication with another bracket having the power small q and that bracket is having the difference of y minus y bar. So these two brackets are in multiplication with f of x comma y into dx into dy. Now here in this particular formulation, the x bar is actually the ratio of m suffix 10 divided by m suffix 00, and the another term that is new to us in this equation, that is y bar, is equal to the ratio of m suffix 01 to that of m suffix 00. So if f of xy is now our digital image represented there, then the equation we can modify giving mu suffix pq computed as summations of the two variables here, one for the x, another for the y here, computed over the product of having the bracket powered small p, the difference of x minus x bar, another bracket having power q, the difference of y minus y bar, into the image digital, that is f of x comma y. So as we are now having the signal as a digital image, that is why from the continuous integrations we have shifted to here the summations. Now the central moments of the order up to 3 can be given by mu suffix 00, that is computed as summation with respect to x and summation with respect to the y, the bracket having x minus x bar that is having the power 0 here, so p we have substituted 0. The second bracket is there in multiplication to this bracket that has y minus y bar. Again this bracket is also provided the power 0 into the digital image f of x comma y. So we simplify it as both the brackets will be simplified to 1 here. The next step of the right hand side can be summation with respect to x, summation with respect to y over f of xy simply. So this gives us m suffix 0 0. Now if we take mu suffix 1 0 for computation purpose, we can represent it the summation with respect to x, summation with respect to the y operated over the first bracket x minus x bar having the power 1, and y minus y bar is the second bracket. This time it has the power 0. So as we have selected p is equal to 1 and q is equal to 0. So these two brackets are in multiplication with f of x comma y. By the next step, thus we can write m suffix 1 0 minus the ratio of m suffix 1 0 divided by m suffix 0 0 into m suffix 0 0. So by the second term we have multiplied and divided m suffix 1 0 by m suffix 0 0, and finally we can write mu suffix 1 0 is equal to 0. Now mu suffix 0 1 can be computed as summation with respect to x and summation with respect to y operated over the bracket having the difference x minus x bar having the power 0, and another bracket y minus y bar having the power 1 here. So the values of p and q in the earlier case have been swapped here, and these brackets are in multiplication with again f of x comma y, our digital image. Now this can be simplified to the next step as m suffix 0 1 minus the ratio of m suffix 0 1 divided by m suffix 0 0 in multiplication to m suffix 0 0. Finally we can write the difference of the two terms is equal to 0. Now we have the computation of mu suffix 1 1 as the summation with respect to x, summation with respect to y. The first bracket denoting the difference between x and x bar is having the power 1, and the second bracket having the difference between y and y bar is also having the power 1 here, and they are in multiplication with our digital image f of x comma y. So as none of the bracket is getting reduced here, we are denoting the next step by m suffix 1 1 minus m suffix 1 0 into m suffix 0 1 divided by m suffix 0 0, and we can further simplify it to the next step m suffix 1 1 first term as it is minus x bar into m suffix 0 1, or we can also write m suffix 1 1 minus y bar in multiplication with m suffix 1 0. Now we have the next computation representing mu suffix 2 0. So it can be computed onto this right hand side by the summations with respect to x and y. So we have the double summation signs here over the multiplication of the brackets, first of all having the differences x minus x bar, so it has the power 2 in this case, and the another bracket that has the difference y minus y bar is selected with the power 0. So in multiplication with our digital image f of x comma y, the next step reduces to m suffix 2 0 minus we have the second term as a ratio of twice m suffix 1 0 square divided by m suffix 0 0, and added with the square of m suffix 1 0 divided by m suffix 0 0. Now it can reduce to the next step m suffix 2 0 minus m suffix 1 0 squared divided by m suffix 0 0, and finally we can denote it as the difference of m suffix 2 0 minus x bar in multiplication with m suffix 1 0. Next to that we can denote mu suffix 0 2 computed as again the two summations with respect to x and y operated over the difference brackets. For the difference of x with x bar we have the power 0 here as the first suffix value, and the second bracket y minus y bar is denoted the second suffix value as a power, that is 2 here. So these are in multiplication with the digital image represented as a function of f of x comma y. So by the next step we can simplify it to the m suffix 0 2 minus the ratio of m suffix 0 1 squared divided by m suffix 0 0, and finally we can represent it m suffix 0 2 minus y bar in multiplication to m suffix 0 1. Similarly we can have the denotion of mu suffix 2 1 computed as again the two summation operations with respect to x and y over the first bracket having x minus x bar that is squared, and y minus y bar that is having the power 1. So it won't be even any effect onto the bracket content, and of course f of x comma y is again there in multiplication. So the final step for the representation of mu suffix 21 we can denote as m suffix 21 minus twice of x bar into m suffix 11 minus y bar into m suffix 20 plus twice of x bar square into m suffix 01. Next to that we have mu suffix 12 computed as again the two summations with respect to the index variables. This time we can say that is x and y operated over the first bracket x minus x bar, having selected the power value 1, that is the first suffix value that we have denoted for mu here, and y minus y bar is selected the power 2 here in multiplication to f of xy as the digital image function. So by the next line we can write it as m suffix 12 minus twice of y bar into m suffix 11 minus x bar into m suffix 02 plus twice of y bar square into m suffix 10. Now we have the next representation of mu suffix 30 computed as summations with respect to x and y. So the first bracket x minus x bar is selected the power 3 here, so it is a bracket cube, and the second bracket is selected the power 0, so y minus y bar to the power 0 can be simplified and reduced here. So these are in multiplication to our digital image represented function f of x comma y. Hence by the next line we can write m suffix 30 minus thrice of x bar into m suffix 20 added with the last term, that is 2 into x bar square into m suffix 10. So by the next representation we have the computation of mu suffix 03. So this is again by the summation operations with respect to x and y variables, where the first bracket into this operation representing the difference of x and x bar is selected the power 0 here, and the next bracket in multiplication representing y minus y bar is selected the power 3 here, and again we have f of x comma y in multiplication to it. So finally we can write m suffix 03 minus at the second term we have 3 into y bar into m suffix 02, and finally adding with the last term, that is twice of y bar square into m suffix 01. So we can summarize these computations that we have made. So mu suffix 00 is nothing but m suffix 00. We have mu suffix 10 is equal to 0. Mu suffix 01 also it has resulted into the value 0. Mu suffix 11 has resulted into the difference of m suffix 11 with the multiplication of y bar into m suffix 10. Next, mu suffix 20 has resulted into the difference of m suffix 20 minus x bar into m suffix 10. Next to that we have mu suffix 02 as m suffix 02 minus y bar into m suffix 01. Mu suffix 30 as a difference of first of all m suffix 30 with thrice of x bar into m suffix 20, and this difference is added with twice of x bar square into m suffix 10. Then we have mu suffix 03 as having the computation of the first term positive m suffix 03, negative thrice of y bar into m suffix 02, and the addition with the positive representation of twice y bar square into m suffix 01. Next we have the last but one representation, that is mu suffix 21 computed as m suffix 21 minus twice of x bar into m suffix 11 minus y bar into m suffix 20 plus twice of x bar square into m suffix 01. And lastly we have mu suffix 12 represented as m suffix 12 minus twice of y bar into m suffix 11 minus x bar into m suffix 02 added with twice y bar square into m suffix 10. Now the normalized central moments that we can denote by eta suffix pq in small cases that can be defined by the formulation. So eta suffix pq is actually a ratio where the numerator is filled up by mu suffix pq in general divided by mu suffix 00 that is having the power represented by gamma here. So here in this equation the gamma is actually a substitution for p plus q divided by 2, and this ratio is added with 1. Now this is applicable for p plus q, that is represented by the value starting at 2, then 3, and this way we can go on increasing the values. Now a set of 7 invariant moments can be derived from the second and third moments that we have represented, and thus we can have the computation of first of all phi suffix 1 as the addition of eta suffix 20 with eta suffix 02. The second is phi 2 computed as first of all the term having the bracket, that is eta suffix 20 minus eta suffix 02, it is squared there and added with the second term, that is 4 into eta suffix 11 square. Next we have phi suffix 3 computed as eta suffix 30 minus 3 into eta suffix 12, that is square, and further added with 3 into eta suffix 21 minus eta suffix 03 squared. Next to that we have phi suffix 4 computed here again in the two terms. The first term is represented by the addition of eta suffix 30 with eta suffix 12, and this addition is squared here, whereas at the second term we have eta suffix 21 added with eta suffix 03 also squared. Now we have the computation of phi suffix 5 represented as the first bracket having eta suffix 30 minus 3 into eta suffix 12. So this bracket is multiplied to another bracket where we have the addition of the two operands, that is eta suffix 30 with eta suffix 12. So this is in multiplication with the square bracket. The square bracket involves eta suffix 30 plus eta suffix 12 squared minus we have the second term in this square bracket 3 into eta suffix 21 added with eta suffix 03 squared here. So this square bracket is completed, and further we have the additions to have the computation of phi suffix phi as the bracket involved thrice into eta suffix 21 minus eta suffix 03, the bracket in multiplication with another bracket having the addition of eta suffix 21 with that of eta suffix 03, and in multiplication with the square bracket that has the first term denoted by 3 into eta suffix 30 added with eta suffix 12 bracket squared minus we have at the last eta suffix 21 added with eta suffix 03 squared here. Now after the computation of phi 1 up to phi 5 we have the sixth computation for phi suffix 6 computed as the bracket having the difference of eta suffix 20 with eta suffix 02 in multiplication to the square bracket as constituting the first term, that is eta suffix 30 added with eta suffix 12 bracket squared minus the addition of eta suffix 21 with eta suffix 03, that bracket is also squared here, and after the square bracket we have the second term representing the multiplication of 4 into eta suffix 11 into eta suffix 30 plus eta suffix 12. In another bracket we have the addition to have the multiplication with this one eta suffix 21 added with eta suffix 03. So the ratio that we have represented the eta, that is applicable with the values selected for p and q here, and lastly we have the computation of phi suffix 7 here as the first bracket involving 3 into eta suffix 21 minus eta suffix 03. In another bracket we have for multiplication, that is eta suffix 30 added with eta suffix 12. The square bracket has in multiplication 2, that is eta suffix 30 plus eta suffix 12 bracket squared minus thrice of the bracket involves eta suffix 21 plus eta suffix 03, this bracket is squared. Square bracket is completed here. We have the more addition with the last term here that has the first parenthesis bracket representing the difference of thrice eta suffix 12 with eta suffix 30. The another bracket eta suffix 21 added with eta suffix 03, and in the square bracket we have the first term given by 3 into the bracket that is squared has the summation of eta suffix 30 with eta suffix 12, and the second term is denoted by the negation sign first of all, and then we have eta suffix 21 added with eta suffix 03, the bracket is squared. Now this set of moments that we have computed right from phi suffix 1 to phi suffix 7 is invariant to the cases of translation, rotation and the scale changes. So let us discuss one example here with respect to the moment invariants. Here the image that we can visualize as a part of figure A, so it was reduced to half size into the figure B that will be followed by. So we have by the figure C part to be the mirrored image at that portion, and further rotated by 2 degrees and 45 degrees as correspondingly shown into the figures D and E here. So here we have the representation of these 5 figures. So images used to demonstrate the properties of the moment invariants. So right from the top we can start for the figure A, then we have figure B, beside to it we have figure C, and in the last row we have figure D and figure E. Now the 7 moment invariants were then computed for each of these particular images as we are discussing the example. So the computations we are getting applied to this image data set, and the logarithm of the results were taken to reduce the dynamic range. So we have one table that shows the result of figure B up to the figure E that are into the reasonable agreement with the invariants computed for the original image shown into figure A. So the moment invariants for the images into the previous figures from part A to part E, here we have this tabulation. So we have the first column representing the invariants right from phi 1, phi 2, phi 3 up to phi 7 in the logarithmic form. The second columns gives you the values of the original image here for the corresponding invariants, and if it is half sized into the figure B, we have the values in the third column. Next to that, as we have the next image that is a mirrored image, so we have the corresponding values. The first value is 6.919, which was for the half size 6.226, and for the original image 6.249. Further, the image is said to be rotated by 2 degrees into the image D here. So for the first invariant phi suffix 1, we have the value 6.253, and for the rotated by 45 degree angle, the phi 1 can be calculated with the value 6.318. So this way we have this tabulation and we can compare the different values in this tabulation. Now the major cause of the error can be attributed to the digital nature of the data, and especially for the rotated images. So this was all about the moment invariants. I hope it is very clear to you people. By the next lecture in the chapter representation and description, we shall be addressing and discussing the topic principal components as feature descriptors. So I hope you are definitely benefiting by the knowledge of digital image processing. If you want to enhance your knowledge for any of the concept and practical sessions in the MATLAB software, and also the practice of miscellaneous problems, you can surely subscribe to our Ekeeda channel. Thank you.